Let's put all this together and look at the function f of x is equal to 5x to the 2/3 minus 2x to the 5/3. We're going to find intervals on which f is increasing or decreasing. We're going to find local maximum and minimum values of f. We're going to find intervals of concavity and inflection points, and then finally sketch a graph of the function. To find intervals on which f is increasing or decreasing, we need f prime. So f prime using the power rule is going to be 10/3 x to the negative 1/3 minus 10/3 x to the 2/3. Let me note that the domain of f is all real numbers. Here we see that the domain of f prime is the set of x such that x does not equal 0 because this negative exponent indicates we have a variable in the denominator. Therefore, x is equal to 0 is a critical number. We'll just set that aside for now. Let's see if we can find any other critical numbers. In order to do that, I'm first going to factor out the 10/3. That's kind of nice how that worked out, isn't it? And then I'm going to express the x to the negative 1/3 as a fraction of 1 over x to the 1/3. So then I have that minus x to the 2/3, and then I'm going to get common denominators. You can verify that gives me f prime of x is equal to 10/3 times the fraction 1 minus x over x to the 1/3. That tells me that x equals 1 is a critical number also. Now, if I want to know an interval over which f is increasing or decreasing, I need to know if f prime is positive or negative. So I like to visualize this using a number line for x, and then I'm going to put all the points of interest that we have here. And so far that is x equals 0 and x equals 1. X equals 0 makes the denominator 0, x equals 1 makes the numerator 0. And what I'm doing here is I'm finding the sign of f prime. I don't really care the value, I just want the sign. So I'm going to pick some number to the left of 0. Let's say 10. 1 minus 10, negative. Let's try that again. I'm going to pick a number to the left of 0, and so how about x equals negative 10? 1 minus negative 10 is positive. Negative 10 to the 1/3 power is negative. F prime is negative to the left of 0. In between 1 and 0, how about if I pick x is equal to 1/2? In the numerator, 1 minus 1/2 is positive. In the denominator, 1/2 to the 1/3 is positive. And so f prime is positive between 0 and 1. And now to the right of 1, if I do pick x equals 10, then 1 minus 10 in the numerator is negative. 10 to the 1/3 is positive. So we have a negative derivative to the right of 1. So for part A, we can say that the graph of f is increasing on the interval from 0 to 1 and decreasing on the intervals from negative infinity to negative, I was looking at negative 10 over there. From negative infinity to 0 and from 1 to infinity. Well, look at this. To the left of 0, my function is decreasing. To the right, it is increasing. 0 is part of the domain. Therefore, I know I have a local min at x equals 0. And then when we look at 1, increasing to the left and decreasing to the right because of the negative derivative, I now have a local max at x equals 1. I'm going to go ahead and box this answer to part A to demonstrate proper technique. And then we'll come back to the whole local min, local max in just a bit. We're also looking for intervals of concavity and inflection points. That means we need f double prime. So I'm going to take this form of f prime that makes it easy to use the power rule on and rewrite it. And let's find the second derivative. We get negative 10/9 x to the negative 4/3 minus 20/9 x to the negative 1/3. Now to analyze f double prime of x, I'm going to go ahead and factor out the greatest common factor, negative 10/9. And then x to the negative 4/3. That's going to leave me with 1 plus 2x. And I'm going to mark on an x-axis for f double prime values that make the second derivative equal to 0, so negative 1/2, or undefined, and so 0. I'm going to pick test points just like we did for the first derivative. To the left of x equals negative 1/2, I'm going to use x equals negative 10. Between negative 1/2 and 0, I'll say x is equal to negative 1/4. And then to the right of 0, I'm going to say x is equal to 10. And when I plug x equals negative 10 in place of x, look, x to the negative 4/3, that 4 is a power. So that factor is always going to be positive. So all I have to care about is the negative in front of 10/9 and whatever sign I get for 1 plus 2x. So if x is negative 10, then I have negative times negative, which is going to give me positive. Between negative 1/2 and 0, if x is negative 1/4, that's going to give me a positive times negative, and so negative. And then if x is greater than 10, I again have positive times negative, and so negative for the second derivative. So for part C, I can say the graph of f is concave up on the interval from from negative infinity to negative 1/2, and concave down on the intervals from negative 1/2 to 0, and then from 0 to infinity. I don't get to say like negative 1/2 to infinity because we have something happening when x is equal to 0. I mean, in this case, that something is that f double prime is undefined, but whether it was undefined or 0, I'm not going to include it in these intervals. But now we were asked about inflection points. And here I can see that we have an inflection point at x is equal to negative 1/2, because an inflection point is a point on the graph where concavity switches between positive and negative. In order to find the value of the inflection point, I've got to put negative 1/2 into the function. You may recall, we also need to know the value of the local minimum and the local maximum. Those go into the function as well. So, or those we get from the function, I should say. So I'm going to put x equals 1/2, 0, and 1 into the function. My calculator tells me that when x is negative 1/2, my function value is approximately 3.8. And we can see when x is 0, y is 0. When x is 1, y is 3. So for part C here, I can say that we have an inflection point is negative 1/2, approximately 3.8. That does it for part C. And now I'm ready to answer part B. We can say that our local min is 0 and the local max is 3. By the way, when we found that we had a local min and a local max, we used the first derivative test. That is, 1 is a critical number. We had the derivative was positive to the left, negative to the right, so we knew we had a local max. That's the first derivative test. Likewise, to find the local min at 0. If we look here at the second derivative, then x equals 1 lives in an interval that is concave down. If I've got a critical number on an interval that's concave down, remember, concave down looks like a cup upside down. And if I have a critical number there, then I have a local max. And if I'm using concavity to answer that, then that's the second derivative test. Notice I get the same answer from the first derivative and the second derivative test. I don't get to use the second derivative test for x equals 0 because that's undefined, and so there's not a concavity situation at 0. So I can't always use the second derivative test, but that's what it looks like. Now, I know this is getting long, but we're going to summarize and then graph. Let's talk about the information that we get from f prime, and f double prime. Our original f was f of x equals 5x to the 2/3 minus 2x to the 5/3. f prime can be expressed as 10 times the quantity x minus 1 over 3x to the 1/3. And f double prime can be expressed as negative 10 times the quantity of 1 plus 2x over 9x to the 4/3. All right, I'm going to get x-intercepts from f of x, which means I'm going to factor out x to the 2/3. We're left with 5 minus 2x. Let's go back to the very beginning. We said that the domain of f was equal to all real numbers. And here we have x-intercepts. We can see that they are at 0, 0, and 5 halves 0. Notice that the 0, 0 is also the y-intercept. We used f prime to find intervals of increasing and decreasing. And what we found was that the graph is decreasing to the left of 0, increasing between 0 and 1, and then decreasing to the right of 1. We said that we had a local minimum at 0, and then we used the function itself, f, to say that the local minimum is 0. We said we had a local maximum at x equals 1, and then again we used the function itself to say that the local maximum value is 3. We then used f double prime to talk about concavity. And we said that the graph was concave up and then concave down and then concave down. We used that information to say that we had an inflection point at negative 1/2, approximately 3.8. This is how we use f, the first derivative, and the second derivative to analyze a function so that we can graph it, which we're going to do now. All right, we got some points we can plot. 0, 0, 5 halves 0, 1, 3, and negative 1/2, 3.8. Just ballpark that one up there. Now, our graph is decreasing to the left of 0, and then the increasing and decreasing part to the right of 0 is pretty straightforward. Concave down to the right of 0. So what that tells me is it's not going to bend up here and do anything like that. It's going to keep going concave down forever. To finish this off, I'll note that our function is decreasing to the left of 0. So it's got to be decreasing the whole time there. And then I go from concave up to concave down. And this is going to be kind of subtle. So I'm going to go concave up here and then concave down here. And like I say, it's kind of subtle, but I'm showing you like a bend that's concave up and a bend that's concave down. But it's not like x cubed or y equals x cubed, because I don't have a horizontal tangent there, right? So I don't want to inadvertently communicate that in my graph. But here we go.